Good morning, friends. In this video, we'll learn how to drive a DC motor using a microcontroller. However, a microcontroller port pin cannot supply the few hundred milliamps required by even a small 3.3-volt DC motor. Additionally, small DC motors are often rated for voltages higher than the operating voltage of microcontrollers. For instance, the GPIOs of NodeMCU operate with 3.3-volt logic levels, while the DC motor salvaged from my old broken printer requires 12 to 24 volt. Therefore, we will need a suitable driver. Let's take a quick look at the specifications of the motor that was used inside a printer to move the scanner sensor assembly. This is a high-torque DC motor that can function with a voltage ranging from 12 to 24 volts. The no-load currents are specified, but with a load, the current will be higher than the no-load current and can reach up to 0.53 amperes. The driver must be capable of driving at least 0.53 amperes. The driver used here is L293D, which is a very popular integrated circuit for driving small motors. This driver chip works with DC motors that can operate in the voltage range 4.5 volts to 36 volts and can supply driving current of 0.6 ampere per channel. There are 4 push-pull output channels in a chip. Let's review the datasheet for chip L293D so we can better understand its features. This integrated circuit has been available from multiple manufacturers for a long time and is still sold by some. I have chosen one available from TI. Note that there is another part available with the same part number but without the suffix D. The suffix D indicates that the part has the freewheeling diode built in for each output channel. When a motor is turned off, the high transient voltage generated is clamped by the freewheeling diode, which protects the driver due to the motor coil being an inductive load. Let's move over to the specifications sections. The first table in this section captures the absolute maximum ratings. Violating these ratings might cause permanent damage to the IC. Please note that the continuous current rating for both L293 and L293D chips differs. The chip with the clamping diode has a lower current rating as the built-in diode is not designed to handle higher power that an external diode may tolerate. The following table captures the recommended operating conditions. Let's quickly review the electrical characteristics of the driver. Note that the output voltage of the driver is usually 1 to 2 volts lower than the supply voltage connected to the output supply pin VCC2. When we connect the VCC2 voltage to a motor, there is a voltage drop across the output driver. Thus, we need to factor in the voltage drop while deciding on the voltage to be connected to VCC2. After taking the voltage drop into account, the output voltage should still be within the specified limits of the motor's operating voltage. The diagram illustrates the pinout of the driver and how to connect the motors for unidirectional or bidirectional movement. In the diagram, the motors on the right-hand side rotate in one direction, whereas the motor on the left-hand side can rotate in both directions. To drive a motor in both directions, 2 driver channels are required, whereas to drive a motor in only one direction, 1 driver channel is engaged. I will use 2 GPIOs of NodeMCU to control the motor and drive it in both directions. The motor shield board used in this video is pre-wired to the pair of port pins GPIO number 4 and GPIO number 0 to drive one motor. There is another pair of pins available to drive the second motor, which I left unconnected. The next useful information is the function table for each driver. The table shows the output logic levels for each combination of logic levels on the input pin and the enable pin. The following section shows the output driver schematics for both L293 and L293D devices. Each driver is a push-pull type, which is also called a half-bridge type. Note that the L293D has the clamping diodes. If an L293 chip is used, as it can supply higher current, suitable clamping diodes must be connected for driving motors or solenoid types of loads to protect the driver output. The last picture in the datasheet shows how this driver chip can be connected to drive a two-phase stepper motor. Let's now proceed to the sketch. It's a basic sketch that activates a motor in both directions for a brief period, and then repeats this process in a loop. The NodeMCU can also be configured to send commands to the controller wirelessly to operate and control the motor, among other possibilities. We can discuss those at a later time. In the given sketch, there are 3 functions defined to rotate the motor in 2 different directions or stop it. The driver's enable pin is tied to high, which means that driving GPIO number 4 and 0 alternatively to high and low will move the motor in either direction. If both GPIO pins are driven low, the motor will stop. In the setup function, the GPIO directions are defined as outputs. The GPIOs are driven low so that the motor does not run at the startup. Then, in the loop function, the motor is driven back and forth every 2 seconds. Let's connect the NodeMCU to a computer using a USB cable and upload the code. I have successfully uploaded the code and the motor is now rotating as programmed. I connected the driver to a 12-volt power supply and observed that the driver output is around 10 volts. Although this motor is designed to operate between 12 to 24 volts, it appears to function even with as low as 6 volts. However, with reduced voltage, the speed of the motor decreases while supporting the same load. By using the GPIO pins that support PWM output, we can control the speed of the motor using analog write function. The first step in robotics is to control a motor using a microcontroller. However, it's important to note that a microcontroller alone is not capable of directly driving a motor. Therefore, it's crucial to choose the appropriate driver for the motor we plan to use in an application. Make sure to select the right driver to ensure proper functioning. If you enjoyed this short video, please consider subscribing to eCraft. Your support is greatly appreciated. Thank you for watching.